It's a pleasure to introduce Siddhartha Santra. He works in the area of quantum information theory. His PhD has been on that topic in 2014 from USC LA. And after that, between 2014 and 21, he has worked at the US Army Research Lab and also together at Stanford University. And he is here amongst us now since 2021 in the physics department. He's also affiliated with the Trust Labs and also for our Center for Excellence in Quantum Information, and Quick ST is the acronym for that. His current areas of interest, which I'll read out, are entanglement structures in large-scale quantum networks, efficient entanglement distribution protocols, and quantum optimization using annealing and QAOA-based methods. I would like to now request Prof. Santra to come and deliver his talk.
Hello, everyone. Thanks for coming. So, artificial neural networks, and the first thing that I did to make this talk was to go to Google and search for Nobel Physics Prize 2024. So the proof is in the pudding. This is what the AI assistant throws out, and it tells you who, what, the who, the why, and the reactions to the word. And if you read it, at least to me, this sounds a little less emphatic than the citation of the Nobel Committee itself for foundational discoveries and inventions that enable machine learning with artificial neural networks. And the operative word here is, according to me, networks. So it's a collection of entities, each of them taken singly might be computationally simple, maybe performing computationally single tasks, but what Professor Hopfield and Professor Hinton did was to look at collective computational abilities of collections of such simple computational units. And a little more precisely, what they did was how to create connection structures between them, and how to create and what should be the dynamics of the individual units such that one achieves what one desires. So this target computational task could be different, but they provided recipes for designing these dynamics and these connections between the different units such that you could accomplish the task. So I think Professor Hopfield was motivated by this basic desire, which is how does mind emerge from the brain? And the distinction here is between the mind, which we can imagine to be the computational ability of a material object such as the brain. And in this paper, which according to him he wrote for physicists, computer scientists, and neurobiologists, he poses and answers this question for a specific computational task. So if you move ahead with the limited definition of the mind, that is the ability to compute in certain special situations, then how does that computation happen from the interactions between the constituents of a material object such as the brain? So here is that seminal paper, and just for your information, this is not a peer-reviewed paper, and it had a strict page limit because it was published by PNAS of 5 pages, including the references. He had to make it accessible to all 3 types of audience: the physicists, the computer scientists, and the neurobiologists. And the essential physical idea here is that if you could encode what you desire out of a computation into the low-lying energy states of a system, then the dynamics would very robustly take any initial state to a nearest energy minima. So it essentially uses collective computation between the different constituents, the neurons. We will come to the structure of neurons in a second. And then it designs the dynamics in a way such that the phase flow of the system, so you start from some point in phase space of the system, and the dynamics would take you to an energy minima. So the the very popular pictorial description of this process is as follows. So imagine you dropping a ball somewhere in this very rugged energy landscape. The ball will somehow find its way to a valley of this energy landscape. And if this valley, the configuration corresponding to that valley, happens to be an information that, for example, you wanted to store in a physical system, then the dynamics of that system, so the rolling down of that ball, has actually uncovered for you what you wanted to retrieve from that system. So in other words, you could encode a memory that you wanted to store in a system as the lowest energy state of a dynamical system, with the dynamics leading you to that point. This picture is also useful to understand other things that can happen in this process. So you can imagine that where you are dropping the ball actually corresponds to an initial configuration that corresponds to information that may be incomplete or corrupt. And so the dynamics of the system actually error corrects for you and brings you to the correct information state. Now, this valley, which acts as an attractor for the dynamics, will only be able to collect dropped balls from a certain region around it, something called the radius of convergence, the radius of attraction. And so this whole landscape, if you imagine extended in all directions, comprises of various attractors with basins of attraction around them. And so depending on where you drop the ball, you are attracted to one of those minimum energy states. So for example, if the pattern that you input to a physical system that we'll come to is something like this, which after a moment's thought is a corruption of J, then the dynamics would be able to retrieve that pattern for you. So in other words, the system would have learned that actually J is what you want to retrieve. It would have become a stored memory. So of course, as I said, this work was motivated by the fact that it also had an audience in terms of neurobiologists. So the brain had to inspire the model that Professor Hopfield came up with, which was a dynamical model for associative memory. So the fact that we associated this figure to J meant that we associate this partial or corrupt information with the correct information. So we made an association between an image like this and the true information like this. So the brain, of course, it was known, this is 1982, and he had already been part of the neuroscience research program. The brain had already been understood as a collection of neurons, and their connections were mediated via physical tissue called the synapse. And each of these neurons, the way it functioned was also understood in terms of how it fired with respect to its membrane potential. So if you imagine what the Hopfield network imagines is a fully connected network of neurons. So there is all-to-all connectivity between these neurons, which in this particular paper were assumed to be bi-state. So bistable, two states, 0 meant not firing, 1 meant firing. So something like this, right? And with this interconnected network of neurons, what you needed was how could you set the weights that would make these neurons interact, and biases which would flip a neuron from a non-firing state to a firing state. So the prescription for these weights and local fields and biases actually were inspired by earlier work. In this case, for example, how the weights are constructed given a set of memories. So VKs represent memories, K, the index, meaning the index K running over the different memories you want to store, and I being the index of the vector Vk. So I, in this case, would run from 1 to 5, but you also had access to a few different memories that you could store in this network. And together this matrix would be, the contribution to this matrix would come from all the memories that you would want to store and their elements. So this learning rule was called the Hebbian learning rule. And if you take this and if you take a prescription for how the network neurons flip from the 0 state to 1 state, the dynamics of the system could be understood as a change in the energy value of the system of neurons for their different configurations. So every configuration with these spins being up or down, 0 or 1, you could calculate its energy, and the dynamics of this network were such that the dynamics would lead to a lowering of that energy till you reached the ground state, till you reach the lowest energy state. So in particular, how the dynamics happened was that each network would look at all its connected neighbors. So for example, this neuron would look at all the other 4 and calculate what this quantity would evaluate to. And if this quantity evaluated to something above a threshold, let's say 0. So if this turned out to be a positive number, it would flip its sign from 0 to 1. Same thing happened for all the others. It happened asynchronously and it happened in parallel. So the only thing that was uniform for all the neurons here was that their mean rate of these updates was some fixed number. So it happened asynchronously, it happened in parallel, but ultimately it would lead to a lowering of this energy such that the system would settle down to its lowest energy state. So as an example, imagine that these were the 2 memories that you had to store. So 1, 1 followed by all zeros, and V2, 0, 0 followed by all ones. If you started the network, so you choose this configuration, you choose 1, 1, 1, 0, 0, so 1, 1, 1, 0, 0, and if you let this dynamics that I just described take over, then the ultimate final point of the configuration for these neurons would be the one that is closest in some measure of distance, in this case the Hamming distance, which is V1. So you would have managed to store this memory in a network of neurons modeled according to these parameters, Hi and Wij. So that was learning. The machine has now learned. One could now make a machine learn certain memories. But machines can do more, and if machines are inspired by brains, they should be able to do more, which is interpret information. So this is where Professor Hinton's work comes in, and he started with this base model of the Hopfield network, but here he arrived at a stochastic generalization of the Hopfield network. So in the previous slide, we saw that the configurations could be labeled by the energy of that configuration. So now, if the probability of the system acquiring a configuration was proportional to the exponential of minus the energy over t, which is a fictitious parameter, this energy being a function of these parameters Wij and theta I, one could imagine tailoring these Wij and theta I, so the parameters of the network, in such a manner that we could get any desired output of configurations probabilistically So any desired distribution of output configurations of this network. Some technical advances here were the fact that instead of all the nodes being accessible to inputs, you had only certain nodes which are uncovered here. So these are covered, these are uncovered. So these would be what are called visible nodes, and these would be what are called the hidden nodes, which basically allowed a more general class of probability distributions to be encoded via this method. So interpretation of information is subjective. Even for the same subject, it could be statistical. And so what this allows us to do, the fact that we could get probability distributions over output configurations of this network, and the choice of our ability to choose these parameters to design these output distributions allowed the machines to interpret information that is fed to them. Just for completeness, let me also say that in this particular paper, 1983, they had a gradient-based learning algorithm for these parameters wij and theta I. It turns out eventually that this is not the most efficient way of interpreting information. In fact, these connections, these all-to-all connectivity between the neurons needs to thin out, and they also need not be recurrent, which is that the action of this influences the other one. So the action of the action of nodes which are neighbors influence each other. This need not be the case, and this influence can be unidirectional, and this can in fact lead to a more efficient way of training, efficient way of figuring out what these parameters should be, and also increase the computational interpretation power of such networks. So taken together, these two results could do this for you. So if you just had a Hopfield network, you could ask it to remember all ducks or all rabbits. But with the ability of the machine to interpret information, you could interpret this as a duck or a rabbit, and you could actually tilt how you interpret that by choosing what this probability distribution of output configurations were. So if you felt like this was more of a rabbit than a duck, you could choose your parameter. You could choose your parameters here such that this probability distribution of the output configurations indeed gave you a higher frequency of identifying this information as a rabbit than a duck. So, as I said, the original generalization, stochastic generalization of the Hopfield model by Hinton was not efficient in what you could do with it, because the way you set those parameters of the network, so the way the interconnections between the neurons, the biases locally at the neurons, they were inefficient to determine. However, if you adopted a more sparse connectivity and unidirectionality in the way these neurons were connected, they came up with more efficient ways of achieving that parameter setting process, something known as backpropagation, which essentially looks at what are the outputs corresponding to a set of inputs, and how far are those outputs on an average over the input ensemble from what you desire as the output. And if you feed back if you feed back information about this divergence between the desired output and the actual output back into this network and try to set its parameters, you would be able to minimize this divergence and make the network output the distribution that you wish. So, in fact, this is where the idea of the deep neural networks comes in. If you stack in more layers, for many problems, it seems the computational abilities of this model increases. There are limits to what you can do with this process. You cannot, you run into problems of overtraining. So for example, if you tell your network too often that indeed this is a rabbit, then it will never classify it as a duck, but which makes the network performance degrade over other similar ambiguous situations. So those are problems that the community is now dealing with. I just want to end with some application that I'm familiar with, some application that is actually an advertisement for one of the later talks, and it is this, where machine learning techniques based on artificial neural networks are leading to design of new quantum experiments. So this is something that I'm not directly related with, but what's happening is that if you tell neural networks of the deep neural network types what you want to achieve in terms of rewards for particular configurations of, for example, optical elements, it will design certain experiments for you. Some of them replicate some optimal quantum protocols. In my own research, we are trying to look at how to make the process of entanglement distribution in quantum networks more efficient, potentially using machine learning, where because we have a very wide space of the possible protocols, we want to give it simple rules to determine what could be the optimal entanglement distribution protocol. And of course, techniques based on neural networks and machine learning were able to predict 3D protein shapes pretty recently, which is a subject for one of the later talks. Of course, there are more uses that we are all familiar with: large language models, assignment writing, automated scamming. But maybe the ultimate test of the ultimate test of this technology would be when it's able to pass the Turing test, when you won't be able to tell the computational abilities of artificial neural networks, at least with regards to a specific test, such as telling apart which is the machine participant in a conversation between two agents, one of them possibly human. So with that, let me thank you for your time.